section we're going to have a look at how data items get to be stored within memory. When we're talking here about memory, obviously we mean the memory is available within the machine. And by way of data, we mean the variables, the arrays, the constants, the things that we create or specify or construct within our programs. Obviously, they're going to be stored somewhere within memory, so we're going to start the process of having a bit more of a detailed look at how that is the case, specifically within C++, although actually this will give us a nice insight into how most programming languages do actually store and access and retrieve and manipulate their data. By way of something that will be obvious to you, when we think about memory, in this particular view, we're viewing it simply as a store of bytes available within the machine. And each byte has an address, a number. And by using its address, we can uniquely and precisely identify whereabouts it is located within memory, and then access that particular byte potentially to read the contents, to change or to write new contents to it. Obviously, when we create variables, they have to be stored somewhere within memory, so it's reasonable to assume then that a particular variable will have a certain location at which it is stored within memory. And when we were looking at the data types, we saw that data comes in different sizes. We might have a byte or a char, an int or a long or a double or whatever, and depending on the type, they use a certain number of bytes by way of providing the representation. So when we're allocating or reserving, for example, an int, within modern CPU compilers, we get 4 bytes of memory at a certain location set aside for holding that particular value. Java, C#, you don't really have any need to worry about where they get to be stored. And in fact, a lot of C++ programs, you don't really need to be worried about that either. But in C++, you can actually ask and then use and manipulate the actual locations. So I can take a variable and I can say, okay, well, tell me the address of that variable within memory. It's useful to ask that when you have an array of data, a collection of these values, because that then lets you change the address, the thing that you're pointing to. But we'll see that when we look at arrays in a bit more detail. So let's give you an example. We've got 2 things we're declaring, an integer counter and a double called total. And whenever the compiler encounters these within the code, it's going to say, okay, I need to reserve or set aside a certain amount of memory for holding an integer and a double. And for integer, let's assume it's going to be 4 bytes. For double, let's assume it's going to be 8 bytes. And you've got a bit of choice here in terms of where you actually declare these and where they get to be stored. But whenever we declare our int counter then effectively turns into a pointer. It tells us the address in memory, that if we go to that address and then interrogate the next 4 bytes, we will be able to access whatever integer is stored within our counter variable. Likewise with total, it also will point to a location in memory, and going to that location we can access the next 8 bytes, and interpreting the information within that as a double, we'll be able to access the value that is stored within our total variable. Now this is all straightforward, it's all simple, you probably already know this, just simply here by way of a reminder in terms of what happens under the surface. Now, variables, yes, can be viewed as having a type and a location. That much is fairly straightforward. Integer variable, its type is an integer. Its location is the address in memory that holds the contents of that variable. And if we modify a variable, effectively what we mean by that is that we go to that particular address within memory and modify the contents of that address. And by accessing a variable, it means that we go to the address in memory that the variable stored and then read and access the bytes associated with that variable. It's simple. This is not difficult stuff. You're probably already quite familiar with it. I flag it up here because in a lot what's going to follow, being able to clearly visualize and to think about these relationships, the difference between an address of something in memory and the contents of that memory, is going to be key to understanding a lot of the types of manipulation that we're going to actually to do. So it is simple, it is straightforward, but it is an important distinction. It's important to keep that distinction in mind. Let's have a look at arrays. So primitive data is fairly straightforward. Arrays, when you're storing a collection of these things, it gets a little bit more interesting. Whenever we actually create an array, and here I'm assuming this is would be known as a raw array, as opposed to maybe the more fancy sort of managed class type arrays you could have, say, in Java and C#. But here we're just talking about an array, a basic raw array. For example, int data4. The way that gets to be realized is that this is effectively a allocation, a chunk of memory that is set aside to hold a total of, in this case, 4 integers. And the compiler is going to work out just how much memory needs to be set aside to provide this. So for example, in this case, probably 16 bytes of memory. It'll be reserved, it'll be allocated, and then associated with that particular array. Important to understand, when we're creating the array, we get a single contiguous chunk of memory. It's not, generally speaking, not chopped up over multiple locations of memory. It's one big chunk of memory, or small chunk, depending on the size of the array. You see example at the bottom. So again, when we refer to data, I mean, data is a variable. It's an array variable in this case, and data will point to the address in memory at which this array starts. And then, because we know the type or the content of the array, we can space out different locations within that, or offset from that, that hold the different element values, the first element, the second element, and so on as we go through the array. So what this means then is that from the point of view of, if you like, the compiler when it's processing or parsing the program, when we encounter an array, there's a few pieces of information that we want to store. So we need to store the array element, what we're storing within the array, the number of elements within that array, and then typically, or derived from the array element, how big each of those array elements are. So for example, an int, generally speaking, is 4 bytes in size. If you have that information, what it means then is that you have a way of quite quickly accessing elements within the array. So when I'm doing an array lookup, what actually happens behind the scenes is there's a quick calculation that will then give me the address in memory of the variable that I'm interested in. And you see the calculation over on the right hand side. So for an array lookup, we go for the address of the first element. This is whereabouts in memory this chunk of memory that's allocated to the array commences. And we add on to that, so we're doing some manipulation here, the array index, if it's the 0, the first, the second, the third element within that array, times the size of each of the array elements. So the example at the bottom then is we've got our array of ints, total size of 4, and we're doing data 2, and we're setting it equal to some particular value. So to calculate this then, I mean, it doesn't start at the beginning of the array and jump forward 1, 2, 3, 4 until you hit the right one. Rather, it knows whereabouts data commences within memory. It knows we're interested in index 2. So then it adds on to the start location 2 times the size of an int. And that effectively then calculates the location in memory that holds the particular array index or array element that we're interested in. This gives you a bit of an understanding then that when we do have an array and we're accessing them, behind the scene we have a quick calculation that looks up and then forms the address that we can go to get the array element that we're interested in. For multi-dimensional arrays, the same story also holds, though it gets a little bit more complex here. Again, it's going to be a single contiguous chunk of memory that gets to be created, but obviously we have to allocate one chunk of memory sufficient to hold whatever number of dimensions we're creating an array with. So an example here of creating an array of chars, size 3, 4. And over on the right hand side, you can see how this is likely then to be set out within memory, where we're starting off storing our 00, 01, 02, 03, 10, 11, 12, and so on. And this sort of illustrates how you can sequence or string it out in one chunk of memory. That holds for 2 dimensions, for 3, for 4, depending on the dimensions you are, you can do exactly the same process. You can probably infer from this then that whilst with a single dimensional array you did a quick calculation to look up the address of a particular element within this, you can do exactly the same thing for a multi-dimensional array. It just involves a little bit more calculation by way of combining the different elements. So for example, even if we do have a multi-dimensional array, we can work out and ask, well, what's the location of the first row or column within that particular array? Again, a quick calculation will provide that. So the same principle holds. Single, multi-dimensional array, knowing where it starts in memory, knowing how many elements it stores, or in the size of if it is multi-dimensional, the size of the different dimensions, knowing how big each element is within it. It gives you a means then of calculating the precise location of each of the elements within that array. Final thing we want to look at within this introduction to memory, and in the next talk we're going to look at sort of extending this to look at some other aspects, but we're going to finish this one off by having a look at the heap and the stack. These are fundamental resources within a program, or locations within which, in memory, within which we can store the variables that we have within our program. Now, memory's memory. You may have 8 gigs, 16 gigs, or whatever amount of memory available within your system. That memory stores everything. It stores the code that we're executing. It stores the variables that we're creating. And it's not unreasonable then to assume if that's the case that we need to have some way to organize, to structure that memory. And we're going to have a look here at a structure that is fairly common on most platforms, really independent of any programming languages. It's more about how an operating system generally structures memory when it is running or executing a program. So when I run our program, what we're going to get, and we can request how big we want this to be, we will get a chunk of memory that is set aside for our application to execute within. That's our memory. It's available for our application to use. Within that memory, generally at the start of it, we will store the instructions, the code that's inherent within our program. So again, it's stored in memory, but there we're interpreting the bytes there as machine instructions that get to be executed. And the loader for the program is going to load in whatever the executable code is and locate it at that first bit within memory. After that then, we have all of the variables and data values associated with it. So code first, data second. It starts off within C++ with an area for looking at static variables. So by static we mean effectively global variables, data that always exists. So immediately after the code we have any of our global or static variables, things that always exist irrespective of the program. So if I declare a global int or static int, then it's going to be allocated a location at this point within memory. What we have after that then is the heap and the stack, 2 things we will be using quite a lot. These are growable and shrinkable, so these change. The amount of code you've loaded in, the amount of static variables you declare, they're fixed when you run the program. But the heap and the stack, they are permitted to grow, to change in size. The heap, it is intended to hold, or holds anything that is dynamically allocated. So it means if I use the new keywords, I say I want to have a new instance of a class or a new array of whatever size, then that gets to be created on the heap. And creating a new instance would mean that I'm increasing the size of my heap, that the runtime will go to the heap, it will create a new, for example, instance of an instance of a class, give me an object, and reserve whatever number of bytes it needs to on the heap. It's intended, the heap's intended to use data for holding data that's fairly long-lived. It's not sort of, you quickly create it and quickly throw it away, but rather you allocate it, you use it, maybe at some point in the future you're going to release it. At the other end, so the heap grows up, at the other end the stack grows down. There in the stack we're using that for holding what's known as automatic variables. So things that generally pop into existence and pop out of existence. So if we call a method, and inside that method we maybe declare, say, an integer as part of one of those internal properties of that method. So when that method exists, that integer comes into scope, and whenever the method exits, we get rid of that integer. So things like internal variables, they get to be stored on the stack. Parameters that we're passing into method calls, they also get to be stored or pushed onto the stack by way of pushing parameters in or getting return values out. So for anything that's this automatic, it's not sort of created and managed by the programmer, but rather sort of brought into existence automatically and then removed automatically, method calls and things like that, they are stored on the stack. And you can see from the two yellow arrows that the heap grows up, the stack grows down, and the free memory, the amount of memory we have available to your application, is the thing that sits in the middle. And should we ever get to a occasion where the free memory runs out and the heap and the stack overlap with one another, then we'll crash with an out of memory exception. Now, we've introduced the concept here of the heap and the stack. When we're having a look at dynamic memory allocation, we're going to be coming back to that, because in C++, unlike certainly to much more of a degree within C++ than compared to, say, C# or Java, you have a lot of control over where it is you get to allocate your data. So I can create instances of classes, I can store them in the heap, I can store them on the stack. I get to choose where it is I want to store them. And there will be important implications for that. But at this point in time, we just simply want to flag up that we have these two different key areas, and they differ in terms of the scope, the type of data that they're intended to hold. By way of summary then, on this introductory part, understanding how your data gets to be stored within memory and arranged and set out is actually quite important to understanding how your program gets to be executed, particularly if you're doing anything fancy by way of manipulation within it. In a lot of C++, this will come down to understanding and thinking about the heap and the stack and things like that, but we'll have a look at those. And dynamic memory allocation is going to be the key part where we will encounter a need to understand this, but all of that's going to be upcoming in the next number of talks.